begin with a word of prayer. So I get up here. Dear Heavenly Father, we thank you for this day. I thank you for break, and just ask that you to guide our steps today. Help us to glorify you, what we do, Lord. In your name I pray, Lord Jesus. Amen. So today we're talking about variation of parameters, and so I'm going to start with the n equals 2 case. And so like the n equals 2 case, we're trying to solve something of the form ay prime prime plus by prime plus cy equals to, whoa, bless you, f. Sometimes I think the book might use a g there. I can't remember. It doesn't really matter what letter we put there. So the idea of variation of parameters is to suppose y1 and y2 form fundamental solution set. What does that mean? So what would it mean to say it's a fundamental solution set? What two things does that mean? The one thing it means, right, is that a y sub I prime prime plus b y sub I prime plus c y sub I is equal to 0, right? For both cases, for I equals 1 and 2. And also, it means that the determinant of y1, y2, right, which is, not the determinant, my bad, Wronskian, the Wronskian of y1, y2 at x, which would be, let's see here. I guess I just decided we're working with independent variable x, so good to know. All right. Sometimes I put a t here, question of taste, I suppose. But we put y1 and y2 in the top row, and then y1 prime, y2 prime in the second row. That's our Wronskian, right? So specifically here, this is y1, y2 prime minus y2, y1 prime. That's an important quantity because we know it's what? If this is a fundamental solution set, the Wronskian has to be, it's been before break, you've already forgotten this. Non-zero, right, this has to not be equal to 0. I mean, we do have Abel's formula, or Abel's formula, depending on where you're from, which says that you can write that in terms of the exponential of a particular integral. But that's what we have to work with, all right? And so the method of variation, well, the variation parameters method, it says to guess that the particular solution has the form v1 y1 plus v2 y2, where v1 and v2 are undetermined at the moment functions. These are the parameters of the method, okay? So we talk about variation of parameters. These are the parameters we're varying. All right? So if this is going to be a solution to star, what do we need? What does it take for this to be a particular solution to star? We need what? We need, if we differentiate this once, then twice, and then we plug it back in, it should work, right? So you guys help me out. How do I differentiate yp prime? So like yp prime is what? So v1 and v2 are unknown functions, right? So I got product rule, I got product rule. And so here we go. We get v1 prime y1 plus v1 y1 prime plus v2 prime y2 plus v2 y2 prime. So you got these four terms. All right? And, excuse me. At this point, we do something kind of strange. We make an assumption about the v1 prime and v2 prime. We assume, so I'm trying to remember. I forget my guess at the moment. Give me a second here. It's been a couple of years since I've taught this, believe it or not. So you kind of got two choices to try to make things zero to simplify things, and the choice which we make, I mean, so this is so we're going to assume that the terms with derivatives of the parameters are zero. Like, so what we're going to do is we're going to assume that this and that, when we add them together, we're going to impose. And you know, this might be too much, right? I mean, like, it could be that we make this imposition and we find out that after we make this imposition, nothing works, right? There's no solutions left. But we're gonna impose this condition on our solution with the hope that that's not too much to impose. Now, admittedly, this is unmotivated, but I've got good company. Your book also doesn't motivate this choice. It just says do this because it makes the solution easier, and that's true. But it does make you wonder, well, why? Yeah. I guess another reason is that if you don't make this choice, then you're going to end up with something second derivative in the parameter. And what's the point in doing that? Because if something's second derivative in the parameter, it's just as bad as the original problem, right? So by making this assumption, we're going to keep from getting second derivatives in v1 and v2 in our proposed solution method. So that's kind of a good thing. We would like the solution method to be simpler than the original problem, you know? So yp prime then is simply equal to v1 y1 prime plus v2 y2 prime. All right, because the other piece is 0 by assumption. And so with this, we get v1 prime y1 prime plus v1 y1 prime prime plus v2 prime y2 prime plus v2 y2 prime prime. All right. And at this point, what we're going to do is we're going to put everything together. So let's, you know, substitute into star. And what do we get? We get, I'll write it out, ayp prime prime plus byp prime plus cyp equals to the forcing function. So there you've got a times, what do we got? Oh no, v1 prime y1 prime plus v1 y1 prime prime plus v2 prime y2 prime plus v2 y2 prime prime. All right, plus what? Plus b. What was my vp prime? Only two terms remained, right? So v1 y1 prime plus v2 y2 prime, if I recall correctly. And and then finally the original guess, which is v1 c times v1 y1 plus v2 y2. All of this is equal to f. So if this is variation of parameters, if this is going to work, this has to somehow work. Well, this has to somehow work. So we have used so far none of our, we've really only used the initial guess, which was that yp has this form, right? Can you guys tell me, though, what we can do here? Well, let me point out this. We could put a times, let's see here. Well, I can pull a v1 out. v1 times a y1 prime prime plus by1 prime plus cy1 plus v2 times a y2 prime prime plus by2 prime plus cy2. Let me underline all the terms that I just grouped together here. So I'm picking on this one, I guess both of these guys, and apparently these guys over here as well, right? All those terms are in there. And what's left? Well, we still got a v2 prime y2 prime plus a, I'll factor out the a, v1 prime y1 prime, I believe. I wrote them out of order. It's because it was closer to me. And all that's all equal to f. So you guys tell me about the stuff I wrote in blue. What can you tell me about that? What's this? And what's this? What do we assume about y1 and y2? We assume they're homogeneous solutions to the problem, right? So by assumption, those are 0, which leaves us with a much nicer problem, right? So we can write it out together here. Let's put together what we got. We got, on the one hand, v1 prime, ooh, this is a nice marker, v1 prime y1 plus v2 prime y2 equals to 0. And we also apparently have v1 prime y1 prime plus v2 prime y2 prime equals to f over a. So the first equation is my imposition, right? And the second equation follows from substituting the solution into the given differential equation. Can anybody here, as you look at this, can you tell me what this is? What are we looking at? It's two equations and two unknowns, right? Notice that you know, the variables here are v1 prime and v2 prime, right? So I can rewrite this as a matrix problem as such. It is y1, y2, y1 prime, y2 prime times the vector v1 prime, v2 prime equals to 0 and then f over a. We're assuming a is not equal to 0 here, of course. Now it's up to you guys. How do you want to solve this two equations and two unknowns? I am personally partial to multiplication by the inverse. What's the inverse of a 2 by 2 matrix? Like what's the inverse of this matrix? y1, y2, y1 prime, y2 prime. Inverse, it's equal to 1 over y1, y2 prime minus y2, y1 prime. Flip the diagonals and put minuses on the off diagonals. That's the inverse of that 2 by 2 matrix. And so if I multiply this equation by the matrix, the inverse of the matrix, I get that, you know, v1 prime, v2 prime is equal to 1 over, you know, y1, y2 prime minus y2, y1 prime times this handy-dandy matrix here, y2 prime minus y2 minus y1 prime, y1. And that all multiplies the vector which is there, which is 0 and f over a. All right, so what does that give me? We multiply the matrix. I'm going to leave that pesky fraction out front. Can you guys recognize what that fraction is? Why is it non-zero? It's the denominator. What? It's the Wronskian, right? And we assume that that's non-zero right here. So we're within our rights to divide by that. And when we make this multiplication, we get minus y2 times f over a. And the other one gives us a y1 f over a. So therefore, dv1 dx is equal to minus y2f divided by y1 y2 prime minus y2 y1 prime. And dv2 dx apparently is equal to y1f divided by, there's an a downstairs, a times the Wronskian. All right, so therefore, v1 is equal to the integral of minus y2f dx over a times the Wronskian. And v2 is equal to the integral of y1f dx over a times y1 y2 prime minus y2 y1 prime. So there you go. Apparently our imposition was not too much. In fact, it was an entirely reasonable condition to put on our solution, because as you can see, we plugged it in, worked it out, and not only were we able to solve for v1 and v2, we find nice cut and dried formulas for v1 and v2 in terms of integrals of the given forcing function and the homogeneous solution set. When can you integrate these expressions? Like when are these going to be integrals which exist? The answer is yes. Yes, they exist, because in as much as f is a Riemann integrable function, we can calculate these integrals. This is a totally general method. What are the strings attached to the annihilator method that I had you guys suffer with the first 5 minutes of class? In order for that to make sense, right, f has to appear, the forcing function has to be a homogeneous solution to some constant coefficient problem. Here, no such strings are attached. Variation of parameters is a completely general method. Undetermined coefficients, on the other hand, is a special trick for special problems, which is easier when you can do it, right? Because these integrals could be a drag, right? Like, let's look at an example. Okay, so guys, I should warn you, there's like 2 different ways of teaching this material. And so some professors, what they do in a problem is essentially make you go through all of this. Like whenever you solve the problem, they basically make you rederive these formulas as part of the problem. I've just never gotten into it. I don't know why, I can't get into it, because I just look at this as a theorem. These are formulas that we have spent 20 minutes of class to derive. Now we know them, right? I mean, you could derive them too if I asked you on the test, right? If I warned you it was coming. Like you might be asked to prove variation of parameters. And I say prove, I just mean go through this derivation, right? It's not actually that difficult a calculation, right? It's, you know, there it is. And so anyway, long story short, there's, you know, I suppose there's 2 different problems in principle I could ask you about variation of parameters. The one would be to derive the method, right? Which is the harder question. The easier question is to apply the method, right? But if you're going to apply the method, you're free to just use these formulas as if they're known, because they are known to us because we just worked them out. All right? So here's an example. Y prime prime plus y equals to secant of x. Now, if you remember integrating secant from calculus 2, this might, you know, strike fear in your heart a bit. As you may recall, integral of secant is one of the more nasty ones. But it's not bad here. So first order of business to do, first of all, just, you know, identify your enemy. This, if you differentiate, what happens? You get secant tangent. What happens if you differentiate again? You get secant squared tangent plus secant cubed, I think. Anyway, it just gets worse from there. If you keep differentiating, it just keeps getting to be a bigger and bigger and bigger mess, right? Which shows you that the naive method for variation parameters doesn't work, right? But more to the point, this is not in the solution set to any constant coefficient differential equation, right? Homogeneous one, at least. So we cannot use method of annihilators on this, all right? So we have to use variation parameters. So first order of business is to find the fundamental solution set. That's easy here. We've got what? Lambda squared plus 1 equals to 0, which tells me lambda is plus or minus I. Therefore, y1 equal to, let's say, cosine x, and y2 is sine of x. All right. Now, of course, you could multiply these by 7 if you wanted to, but why do that, right? Sine and cosine will do. By the way, I could have said sine then cosine. That wouldn't matter either. You just make a pick. You make a choice. Make a pick, right? Okay, great. Next thing, since we know where we're going to be calculating these formulas. Before you get to these integrals, you calculate the Wronskian and simplify it. First, do that. All right? So what is y1 y2 prime minus y2 y1 prime? So this is like, cosine x times cosine x minus sine x times minus sine x. Well, look at that. This is 1. So the Wronskian's 1. What's a equal to in this problem? A equals to 1. So let's calculate. What's f? This is my f right here. All right, that's the forcing function. By the way, I'm hoping to spend the rest of the week mostly talking about applications, if everything goes as I hope. I mean, I got a little bit more solution technique stuff I could tell you about, but hopefully that won't eat up too much time. All right, so v1 then is the integral. So basically, long story short, these denominators are just 1 for this example, right? So we just have to integrate minus y2, which was what? Minus sine of x times the secant of x dx, and v2 is the integral of cosine x, ooh, I like this one, times secant of x dx. All right. So here we have minus the integral of sine x dx over cosine x. And here we have the integral of dx. All right. So this is minus the natural log of the absolute value of cosine x. And this is x. If you add constants here, that folds a copy of the homogeneous solution into the particular solution. So I just don't usually add constants because I like to add the homogeneous solution separately. Here it is. Thus, y equals to c1 cos x plus c2 sine x minus, let's see here, v1 times y1 is cosine x, natural log the absolute value of cosine x, plus x sine x, I think, if I did it right. Let me write out what I just did underneath it. Tell you what I'm up to. So I've made some bad decisions teaching at 8:15 this semester, here and there, like that calculation of the 3x3 Wronskian. I have regrets, So this here is yp, which is v1 y1. So I stopped myself from doing such a thing today because I'm going to show you on the projector what this looks like for higher order. But this is the v1 is the minus log cosine x, and the y1 is cosine x. Here the v2 is x, and the y2 is sine x. And lo and behold, there it is. This is the general solution right here, guys. If I was given initial conditions, how do you apply them? While we're waiting for this thing to come to life. It's like if you knew y of 0 was 1 and y prime of 0 was 0, do you apply these initial conditions just to the part with C1 and C2, or do you apply it to the whole general solution? What do you think? The whole general solution. Very good. So we'd have like, yowzers. Y of 0 would be C1 times 1 plus C2 times 0 minus 1 times natural log of 1, also known as 0, plus 0 times the sine of 0, All right, so all of that just to say that equals to 1. Therefore, C1 is 1. I regret doing this. Then I need to differentiate to figure out C2, right? So to differentiate, we are going to have to do the product rule, right? Which we know because we all took calculus, I think. I mean, I'm pretty sure we took calculus, right? Let's see here. At some point. I bet your calculus is better than my calculus. Let's see here. I had independent study over the summer with a really nice lady, but she didn't know calculus. Let's see here. Come on. There you go. All right, so y prime is minus c1 sine x plus c2 cos x minus sine x, actually plus sine x log of the f of I cosine x minus cosine x times minus sine x divided by f value cosine x, I suppose, plus 1 times sine x. Goodness gracious, I regret doing this. Plus x cosine x. But I think if we look at y prime of 0, only like, well, c2 remains. That's 0. This is 0. 0. Everything's 0 except for c2. Oh, so c2 is 0. Okay, well, it was kind of anticlimactic. So yeah, a lot of differentiation, but basically what happens after the dust settles is you find out that c1 is 1 and c2 is 0 to fit these initial conditions. It doesn't always have to happen like that. Usually the particular solution will interfere with how the story plays out. So this is an unfortunate example in that regard. All right. So I would draw your attention to the fact that I do have oodles and oodles of examples in the notes of, like, you know, the method of undetermined coefficients, right? Obviously, I do not have time in class to work out a bunch of these because it takes a long time to work out even one of these. But the method is always the same, right? So like this one, I have y prime prime plus 4y prime equal to cosine plus 3 sine. Double equals here. That's mysterious. That's a typo. But let's see here. So like the homogeneous solution here is a constant at e to the minus 4x, neither of which you see. Oh, wait a minute. Actually, part of which you see, the one overlaps with the homogeneous solution, right? So for that reason, I put an x times the c to deal with the overlap. So this can be derived by the method of annihilators, but I just write it down there. So that'd be like your quiz problem. You just write it down. You were not supposed to be doing all this kind of stuff in the quiz. Obviously, there's not enough time to do that in 5 minutes. So once I have the form of the particular solution, I plug it in, and then I equate coefficients of the functions which appear, in this case cosine, sine, and 1, and it gives me these 3 equations. And they're, you know, it's 3 equations, 3 unknowns, but they're usually pretty easy to solve. In this case, c1's a fourth, and these are 2 equations, 2 unknowns, which you can work out to give you, you know, minus 13/17 and 1/17. So here's an example of, you know, the method of undetermined coefficients. My point to you is there's another there's a bunch of examples in the notes to look at. If you don't understand the method yet, please look at the notes. So like here's one. If you've got sinh, right, and there's no overlap between sinh and your homogeneous solution, then this will work. So the homogeneous solution, I'm living dangerously here, right? Because I don't know what's the homogeneous solution of this thing. Well, it's what? This is lambda squared plus 5 lambda plus 6, which is lambda plus 2 times lambda plus 3. So the homogeneous solutions are e to the minus e to the minus 2t and e to the minus 3t, neither of which are parts of sinh. Like sinh is a funny way of writing a linear combination of e to the minus t and e to the t, you know? So if I had lambda equals to 1 or minus 1 in the homogeneous solution, I would need to consult expert advice. I'd need to use the annihilator method to craft the proper solution. Not needed here, so I can just go with the naive solution of a cosh plus b sinh, plug it in, and then equate coefficients, and we get that. So anyway, I'm hoping after you guys finish your homework that it's kind of, you know, more in your system. Now, so I just worked out variation parameters for n equals to 2 in class today, right? We could work that out by hand. It wasn't too bad. It turns out, though, that this method is totally general. It works just as well for the order n problem. In the order n problem, you have a fundamental solution set of y1 through yn. And so your variation parameters guess would look like this: v1, y1, v2, y2, all the way out to vn, yn. And then you differentiate it. And then you would impose that the terms with derivatives are 0, sum to 0, in order to not get higher derivative constraints on the variation on the parameters. So we just like we did before, we make constraint 1 be this. And then we differentiate again. And we get all this. And this time we make another constraint. We make the constraint that all of this has to be 0, as again to avoid higher order conditions on our parameters. And guess what we do? Then we differentiate again. And once more impose the condition that the terms with derivatives of the parameters have to sum to 0. Ultimately, we get the n minus 1th derivative is equal to the sum of these derivatives. And that we plug into the differential equation, which I had the good sense to not try to do on the board today, because when you do that, well, you'd get this, among other things. So this will derive for you that the nth derivative is equal to that. So anyway, let me get to the point here. After you plug everything in and impose the n constraints and calculate a bit, you can rearrange it as a matrix equation. And the derivatives of the parameters, so this time you've got n parameters, all first order differentiation, and the equations that you're picking up are exactly the Wronskian for those n solution sets. So you know that this is an invertible matrix, which means you could use your favorite method to solve for the v1 prime, v2 prime, whatever. Like some of you guys maybe like to use Cramer's rule. We could use Cramer's rule to solve for any one of these. What's Cramer's rule look like? It says you take, you know, to solve for the jth one, you take this, you swap out the jth column, you replace it with this in the jth column, you calculate the determinant of that, and then you divide by the determinant of this. That's equal to vj prime, right? Then you can integrate that. So here's a, well, this is just an example of what Cramer's rule is for a specific, just plain old linear 3x3 system, in case you didn't know. I do think that gets covered in some engineering classes, but I don't think all engineers have it in all their classes, you know. Anybody seen Cramer's rule in a class? No? Oh, wow. Interesting. I used to have to fight engineers to not use that in linear. But I guess things have changed. Whatever. But it's not especially important. It's not my favorite rule. But Cramer's rule does give you these formulas. So this is the nth order variation parameters, where W1 is formed by taking the Wronskian and swapping out the first column for the column that's mostly the B vector here, like that. I have a token example of this monstrosity. Well, okay, this is not the monstrosity. So first of all, if you look at n equals to 1, I think this just reduces to the integrating factor method, actually. So at n equals 1, this becomes the integrating factor method. N equals 2, we worked out today. There's your handy-dandy formulas. N equals to 3 and 4 and higher, I don't write down formulas for, but I do have an example here. Y prime 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 plus y prime equals to x log x. So you have f equal to x log x. You get fundamental solutions of 1 cosine sine. Thankfully, the Wronskian is, I think it's still 1. But I call these sub-Wronskians. The sub-Wronskians are not 1. They're this, this, and this. As you can see, I'm swapping out the first column or the second column or the third column for the inhomogeneous vector. And so we are, it's not always easy to get agreement amongst the instructors on what exactly should be covered in all courses, but there is wide agreement that we should not test on this. And I agree with that because this is horrible. And if I assign these problems, then I also have to work them out, and I just don't want to because they're quite horrible. I'm just talking about the order 3 and higher case. I wanted to present this to you, though, in part for the logical completeness of the argument, because this is a completely general method, and it shows you that you can find a particular solution to the non-homogeneous problem, even for the order n case. Like variation parameters is totally general. It's just ugly for higher order cases. Another fun thing to do, I had one other example to share with you guys here for variation of parameters, which is this one, y2 prime prime minus y2 prime plus y. So this one, we get characteristic solutions, fundamental solutions e to the x and x e to the x, because we have characteristic value 1 repeated in this problem. And the Wronskian here is not 1. It actually simplifies. Notice I simplify it first. We get the Wronskian's e to the 2x. So my variation of parameter formulas look like this and that. And when I plug in f, I get this and that. And so I also wanted to tell you about this. Sometimes if I want to test variation of parameters, but I don't want to test you guys on your ability to integrate, I will ask for an integral solution. What does that mean when somebody asks you for an integral solution to a problem? Yeah, that's right. So that's license for you to leave your answer as an integral. That's what that means. So this is the answer, because until I give you details about f, that's as far as we can go, right? As far as you can go. If I did know that f of x was e to the x sine x, then I could plug those. Then I could plug those in there and try to do the integrals. Yeah. Oh, I guess it's not too bad. The e to the 2x it'd be canceling, and we just get this. Yay! Which, of course, in this case, like, could you solve this problem with without variation parameters? If I have y prime prime minus 2y prime plus y equals to e to the x sine x, could I solve that without variation parameters? I surely could, because e to the x sine x is from lambda equals to 1 plus or minus I, which is very much a homogeneous problem. Yep.
So for us to find the general solution, we can just assume it's the integral solution?
That, if you're not getting enough info, that's like all you could do. So like I would typically, if I was just interested in the integral solution, I would not give you enough information and kind of force you to do this, basically, right? So, all right. So I have a take-home quiz for you guys. Like a twofer, wow. Yes, a twofer. And we will talk about part of this together before you guys leave. So this is due Wednesday. I don't think this is going to take too long. Really shouldn't. One of the problems is variation parameters. The variation parameters problem is a secant. It's not the same problem I worked, but it's awful close. So what I wanted to do, though, I said hint, see the solution to quiz 7. So just in case life gets crazy and I don't get that solution posted in a time which is convenient for you, let us work out the particular solution, the form of it, for problem part B. All right, so let's work it out. Part 1B. We're up against the clock. No. Y prime prime minus 9y prime equals to x e to the x. All right. Oh, plus e to the x. That's kind of different, isn't it? So I've got d squared minus 9d acting on y is equal to x plus e to the x. This thing, I can make my annihilator d squared, that kills the x. And then d minus 1 kills the e to the x. This factors as d times d minus 9. So if I look at LA, excuse me, AL equal to y, I get d squared times d minus 1 times d minus 9 acting on y equals to 0 because the a kills off the x plus e to the x. Before we go further, simplify. We must do the algebra, right? We have to simplify. So what's common here is this and this, right? So I've got a d cubed times d minus 1 times d minus 9 acting on y equals to 0, which tells me the general solution has the form like c1 plus c2x plus c3x squared plus c4 e to the x plus c5 e to the 9x, I believe. All right. Let me circle the things we don't care about. This guy and that guy are homogeneous parts, right? So to solve this problem, and this is not the solution to the problem on the take-home, right? This is just the start of it. Yp, you're going to want ax plus bx squared plus c e to the x. I believe that is the form that you want for the particular solution. This was the answer to part B on the quiz today. That's the form of the, I asked for the minimal form. The minimal form for the particular solution does not include these two pieces, right? Just that. That's enough to capture the forcing function x plus e to the x here. All right? So, and again, the third problem on the quiz is, I think, y prime prime plus 9y equal to secant. Was it? Oh, wait a minute. Turn it over. What does it say? I did secant 3x. That's important. If that was secant x instead of secant 3x, that is a far less friendly problem. I'm trying to be friendly. Anyway, see you guys Wednesday.